Thank you. Hey guys. So this talk is about finding zero days or vulnerabilities in embedded system using coverage-guided fuzzing. Okay, so we have two speakers here, and okay, my name is Quinn. I'm working in Nanyang Technological University in Singapore, and my research area is mostly focused on low-level systems like OS or virtual machine or binary analysis. And I happen to be the founder and the maintainer of a few reversing frameworks like Capstone Disassembler, Unicorn Emulator, and Keystone Assembler.
All right, my name is Kaijun. We've been working together for many years, and I guess this is the first time we are actually on the stage together, presenting our work together. So, yeah, that's why I'm here. I'm working for JD.com, e-commerce company. So we design, and me and my friend, we designed quite a fair bit of badges for security conference. So that is part of it, mainly for Hack in the Box. And I am from Hack in the Box, so I'm the crew. Our next conference for this year, that will be in Beijing on early November, and the late November, we will have one round in Dubai. All right, unfortunately, the CFP is closed, so nothing much I can help over here. Okay. And then, yeah, some of the conferences, some of the things that I've done before. So that is basically what about me. All right, so pass it back to Quinn.
Okay, so here's our talk. First, we introduce a little bit on the background on coverage-guided fuzzing and how does it work for embedded system. And then we can show you a few programs if you want to introduce smart fuzzer running on embedded system. So we show each of these programs. We need to emulate firmware, we need to build our own DBI for instrumentation, and then we go on to build our own fuzzer running on embedded system. And there's some demo. Okay, so first part about fuzzing. The idea is very simple. Fuzzing is a technique for you to automate software testing to find bugs. So the diagram you can see on the screen. We run the fuzzer by feed the graph input data to the program that we want to test. It's an archive loop. And when the program is running, we monitor it to see if there's any errors like crash or hang or memory leaking. And if we focus more on exploitable bugs like memory corruption or information leaking, we can find vulnerabilities. So one of the most important things for all the fuzzer is that they need to generate the root input. So when the program runs on that input, it can exercise as many code as possible. So on the other hand, all the fuzzer need to maximize code coverage to find bugs. So essentially, there are three kinds of fuzzers. First one is black box fuzzing. This kind of fuzzer is pretty simple. So the idea is that we randomly feed the input to the program that we want to test without knowing what's going on in the program. So we don't know what's going on. Just feed a random input, and hopefully you get some crash. So of course, this kind of fuzzing, the black box fuzzing, is very simple, easy to build, but it's kind of dumb and cannot find bugs that stay deep inside the program. So the next type of fuzzer is white box fuzzer. So this kind of fuzzer, we use many complicated techniques to analyze the program before we test it. And because we know very well how the program is structured, we can generate a better input. So white box fuzzing is nice in theory. It can find bugs, but in reality, analysis on static program is not easy, and it's too complicated. So eventually, white box fuzzing is too heavy to run. It's too slow. So come to the next one. The last one is gray box fuzzing, or we also call it coverage-guided fuzzing. So the idea is very simple. So when we run the program that we want to test, we do not run it as is, but we instrument the program. So when the program is instrumented and we run that on the input, the instrumentation tells us what's going on, the progress of the program. And based on the progress of the program, we can generate a better input. So we can see that coverage guided fuzzer is kept somewhere in between white box and white box. It's much smarter than white box because it knows what's going on. But on the other hand, we do not rely on very heavy and complicated techniques for binary analysis. So guided fuzzer proved to be very effective and it found a lot of bugs in the last few years. It's easier to use, easier to set up, and really find a lot of bugs. And one of them is fuzzer of this type is American fuzzy loop or AFL. And AFL in the last few years found a lot of bugs. So the idea is that AFL follow exactly this diagram. So you need to instrument the program so AFL can find the bugs. But the idea is that AFL rely mostly on program with a source code. So to test and to find bugs in program, you need the program with the source code first, which is open source first. And then AFL use its own compiler to, so when you use the AFL compatible compiler to compile this program, this compiler automatically introduces instrumentation into the program. So at the output, you have the binary that's already instrumented. Okay, so that's the idea behind the coverage guided fuzzer. But the thing is that guided fuzzer was introduced for very powerful PC system. So once you have some program with a source code, usually people use guided fuzzer like AFL and compile this program to run on PC. We don't run this one, we don't test this one on any embedded system like ARM, ARM64 or MIPS. We don't do that because the PC, the Intel CPU is much more powerful. So you can run the fuzzer at much faster speed. So it's more productive to find bugs. So now the question is that if you want to bring this technique guided fuzzer to embedded system, how we can do that? So turn out that is not very easy and there are many issues. First of all, embedded system has very poor support for introducing new tools to run on top of that. And embedded system, in many cases, are not open source. You don't have source code. And they have very poor support for embedded hardware on the existing guided fuzzer. So we go to the detail on these issues. First issue is that embedded system is a very restricted system. So on the embedded system, we do not have built-in shell access. So you cannot access to the shell and log into the system like a typical PC, right? And in the embedded system, they do not give you any development facilities. So you can build the new tools, build a new fuzzer. For example, inside the embedded system, usually they do not provide you the compiler. They do not provide the debuggers or any analysis tools. So that's the first issue. The second issue is that in many embedded systems, you do not have source code. You have binary only. You have firmware and binary only. You have no source code at all. And it turned out to be a big issue because on the existing guided fuzzer, they rely on source code to be available, for example, AFL. So you need source code, so you can compile source code and instrument the program, so you can do the feedback fuzzing. To be fair, AFL support binary fuzzing using some emulation mode like QEMU. But QEMU mode, when done on AFL to fast binary, is very slow, it's not reliable, it's very limited in capacities. And we share issue for many other tools based on DBI. So the last issue is that most existing fuzzer is built for Intel CPU only. They have very poor support for embedded CPUs like ARM, ARM64, or MIPS, or PowerPC. So for example, you want to fuzz a binary, right? We need to use some DBI, some dynamic binary instrumentation framework. And all of them mostly built for x86. For example, we have PIN, right? PIN from Intel. They support mostly Intel CPU only. They have very poor support for ARM, and there's nothing for ARM64, MIPS, or PowerPC. The other very popular framework is Dynamorio. It's only support Intel. and very poor support for ARM and nothing for other CPUs. So we have many problems. We want to introduce a guided fuzzer running on embedded system. So how to show each of these problems to build our own fuzzers.
So, all right, my turn. We're going to talk about our firmware emulation and why firmware emulation is, we do have a very limited resources when it comes to our embedded system, so we need to emulate, and then in order for us to put in more tools. So before we start all these things, the first thing we want to talk about is SoC, all right? We are not going to talk about MCU over here. So we used to have PC during the olden days, and then we started to have SoC. So that is where they, or the vendor, can start to build ARM MIPS, ARM64 devices, all right? Step by step, chip by chip, okay? Just like the board up there, for better, lesser power consumption, better performance devices, cheaper. So everything is scaled down from PC, including security. So this is what we are starting at, all right? So in order to play with all these things, okay, Quinn started a fuzzer, and then he tried to run, and then I guess he's lacking of a friend that can do hardware. That is the reason he comes to me. I guess. Quinn, is that right? Okay. Okay, so the requirement is you need to know quite a fair bit of knowledge on hardware, PCB design, how does the chip runs, okay, of course GNU commands, and you need to love hardware and not only hardware hacking. That is very important, all right? And I got questions, all right? So when you're talking about hardware hacking, you're talking about hardware design, it's always something that once you cross over, there's things in the darkness that can keep your heart from feeling the light again. Who knows where does this race comes from? Nobody watched Black Hat. Nobody watched Raymond Reddington, obviously, all right? So, okay. So the first thing is we wanted to test our fuzzer in a actual firmware situation. So I brought up a development board, something like this, okay, running on a MTK chipset 7621. It's a very, very powerful chip that can build a very nice Wi-Fi modem. We tested, we ran. Our result is not really promising due to the MIPS, due to the design of the core. So we thought that maybe we can go a bit further. So we got a generic OpenWRT runs, and then we tried to build something on top of it. And then we thought that why not we try to get some real firmware and try to run it and try to fuzz it. So this is the thing that we are trying to do. So our idea is very simple. We extract the firmware. It's either from the flash, the website, or from the APK. Some of the Android's APK, of course, we don't touch those IPA files. Some of the Android APK actually comes with the firmware, okay? Or we try to sniff a traffic, put in a man-in-the-middle proxy, all right? And then we try to extract the firmware. So this is how we get it, all right? So one method is to get the firmware. We extract it, we get it from the APK, we go to the official website, all right, to download the firmware, which is possible for a lot of security cameras, a lot of routers, a lot of IoT devices, okay? Or we need to do some chip off, take out the flash from the device, okay? And then we need to extract it, we need to patch it back. So, or we need to go into some third-party modding website that actually provides the original firmware. I got no idea how they do it, but apparently they got it. So these are the things that that we do. So technically, if you want to own the hardware, it's very simple. You download, you patch with a backdoor, you flash, and then you're gone. So our idea over here is what if we really wanted to get a remote code execution? That is one. And number two is we want to fast and see what is more. And especially from a country that I'm working in, I'm from Malaysia, but I'm working in China right now. From that particular country, you can have a lot of hardware with some really, really interesting backdoors, okay? Don't quote me. I still want to go back to China and work, all right? Okay. So, previously I told Queen the easier way is Raspberry Pi Zero can do a very good job on ARM environment, all right? And if we wanted to test on Arch 64, which is ARM 64, we can use a Raspberry Pi 3. That can give us a very good platform on Arch 64, okay? MIPS is a bit challenging, but there are tons and tons of development board that can actually help us to run different kind of MIPS devices. So, how many kind of MIPS devices that we need to purchase before we can test our fuzzer, all right? So that is question number one. Okay, for me it's very simple. I just order from, China website and then they'll send it to me like yesterday if I order today. So that is what in China. Okay, Raspberry Pi is rather simple, but along the way we discovered that if we are using ARM or ARM64 to emulate certain firmware, it's going to give us a lot of issue. One of the issue is the sharing libc is not really compatible with the one that they have due to the different version that they compile, due to different platform that they're running, due to different SDK that they build from different vendor. So that is one of the major issue that we are facing right now. So I told Queen, in order to move forward, we need a universal platform. Okay, something that I can work in when I was in China, when I'm still in China, and he can work together when he's back in his own country. So this is the thing that we wanted. We don't want to ship hardware back and forth just for the testing. So, yep, we try to figure out the way. We wanted to do a virtualization so we can test our fuzzer to prove that our fuzzer is strong enough, to prove that our fuzzer is fast enough. And the main thing with the fuzzer, the main thing with the virtualization is we can add 1 or 2 or 3 or 4 cores into the virtualized machine together with hypervisor. Okay, we can add more RAMs. Okay, due to the design of the spec of the original SoC, okay, we can add in more space, all right, not the traditional 8 megabytes, 16 or 32 megabytes or 256 megabytes limitation. So these are the things. Because when we tested with especially MIPS or the original hardware, all right, if we try to burn in a firmware, OpenWRT or whatsoever, the 8 megabyte limitation, the 16 megabyte limitation really give us a lot of issue when we try to put in our tools, we try to put in our fuzzer, we try to add in more libraries, okay? So, and the most important thing over here is we don't have apt-get inside all these devices. You do have for Raspberry Pi, but you cannot really analyze those kind of old firmware in Raspberry Pi. So we need apt-get, we need to install all kind of tools. We really don't want to do cross-compile with all these hardware devices. It really killing our time. I mean, we got better things to do in our life, all right? So, yeah, by running on a virtual machine that actually give us more resources, more flexible resources, more powerful thing, and more space to run our code. And the entire objective, okay, to run all these commercial devices without source code, and in order to allow us to fast, is always we need to get one process running, okay? Yes, I'm lying. Normally 2. But one core process and one supportive process. I will explain why later. So most of the time, when you open up the main process, it always spawns the listening services, whichever port that they listen. They always compile Apache in there. Not really Apache. They compile the web server in there. They have their telnet in there. They have all the services in there. So there's always an argument when I talk about this, okay? There are some CTF players, when we talk about only need one process running, people always say that you can actually use QEMU static to run it. QEMU static-ARM to run the entire process. But no. QEMU static allow you to run one process, and you cannot interchange certain information with the sub-process, all right? The sub-process simply means when a vendor design an IoT device, regardless of whether it's CAM, it's Wi-Fi, or whatever thing there is one process that handling all the listener, all the demons, all right? And the other process will talk to the hardware, especially if you try to analyze or when we try to fuzz smart speakers, right? It's regardless of whether Amazon or those Chinese-based speakers. There are one process that talk to the hardware, pass in the configuration, and the main process will started to pick up the information and start the listening devices. So if you're using QEMU static, you will not be able to achieve the intercommunication between the two processes. And during our research, okay, we tried to boot up the entire firmware. We discovered that there is a couple of solutions, okay. One of them, of course, is this one. It's called FirmDyne, all right. But very nicely done, but it's very heavily rely on SCOR's FS. If you move out from there, you cannot actually do anything, and it's very good for dealing virtualization, but anything out from that particular field model of modem, it doesn't prove any help, all right? And if we search for more, we discovered that people used to run it on a very simple way, okay? 2016, there's one guy actually posted a video on how to do, how to run different kind of ARM firmware or MIPS firmware, but due to the requirement and the changes on daily for the internet access or different hardware that you need to fit into the firmware, it's not easy to run. So once we are able to run out, okay, including hypervisor, which is very, very important, okay, that will make the entire system faster, especially for ARM. Once we fix this part, we discover another thing that we need to fix, which is to run the firmware, all right? Like what I mentioned just now, the libc, the different kind of a library is actually very, very hard for you to fit in the entire system. So we thought, chroot, it's a very, very easy development. In fact, a lot of ARM exploitation training still rely on chroot to make sure the daemon runs properly. Yes, I totally agree that can be done. Okay, but if you want to attach with some other tools, okay, GDB or whatever thing there is, what are the tools that can actually help you? I still don't really like the way on running a GDB server and then try to connect it and do all kind of weird stuff over there. So I always wanted a more easier way. All right. So in order to fix this few issue in virtualizing environment, I want to run the thing as native as possible without chroot. Okay. I don't want to run in a virtual environment and chroot again, dream within a dream. All right. That is what we wanted to achieve. So we try to run in a native QEMU system, okay, for that particular architecture. The first thing that we bump into is this very weird found, not found issue. We try to run a binary, okay, so we try to run a bin bash inside the system, okay. We have our virtualized environment, we download the firmware, we unpack the firmware, and then we saw this, it can be bin bash, it can be bin sh, for BZBox fake bin bash. It's not actually bin bash, it's ASH, but they just wanted to call it bin bash. So we try to run it, and then it says found, not found. And we try to troubleshoot for quite some time, and we discovered that the first library is actually being required. So how do we fix this? Is we do a LD and we do a LN, we do a soft link, and we get past the first level. Okay. It says found, not found. The binary is there, but it's actually the core SO is not there. So that is the first thing that we face. Okay, and we got more library issue. Okay, so the first thing is once we move out from the chroot, we need to soft link all the required library, okay, one by one, or different kind of a BZBox command, which you can see from the screenshot. Is search for 1, is search for 2, is search for 3, 4, and all kind of weird BZBox settings, okay. So once we soft link all the things, okay, then we are moving nearer to the process that we can actually executing. That is number one, okay. And there are some certain issue, they will just give us a seg fault without telling us what is missing. So we have issue number 1 is found not found. We have issue number 2 which will tell us which file is missing. The third issue is seg fault. So we need to, the easiest thing is always S-trace, okay? So we S-trace the process, and then we discover along the way there is some file missing. We need to again patch it, we need to soft link it before we can get the process running. So that is number 2. And then once we finish all this part, we discovered that the interaction with our NVRAM, okay? So anybody knows NVRAM? No. It's a place for you to store. Your configuration inside your hardware. So the dark side for the entire NVRAM is it relies on one process. So I did mention earlier just now, there's one process that talks to the hardware, talks to NVRAM, and they will pass information to the main process for them to spawn the actual daemon listener. So we spent quite a fair bit of time to try to craft NVRAM and try to make try to emulate NVRAM. Obviously, we fail. We are not hardworking enough. So the next thing we know that is we should emulate the process that actually pass the information of the NVRAM into the main process. So we solve the issue over here. Okay. So sometimes the main process, it's not really look for the configuration. If they did not discover the NVRAM, they don't have the configuration, the main binary will self-create a set of configuration for the system. So if you are into that kind of binary, congratulations, it's very easy. You can run the binary as and when you want it. Okay, so fake NVRAM is always, how can I fake the NVRAM? The communication between the hardware connector and the main system is always using a UDS, Unix domain sockets. All right, so write a Python script, doing the put in the Unix domain socket, return them whatever information that they need into the main binary. You can get the binary running as and when you want it, anytime. Okay, so done. And now one of the very weird thing is wireless devices. Okay, smart speakers, routers, wireless cam, okay, they need to run WPA configurations, okay, wireless configuration. So we discovered that we need to virtualize some sort of wireless devices in there, but I was lazy enough to make ETHO, rename it to WLAN0, and suddenly a lot of devices works inside the emulating environment. So the moral of the story over here is that you don't have to emulate or try to simulate whatever hardware that you have. You just try to fit in the things that they think is good enough for them to run and to spawn the process before you can actually analyze it. Okay, so we talk about library feeding. We talk about feeding NVRAM. We talk about wireless devices. If everything else still fail, okay, just patch it. All right, this is your last resort. So there are certain parts that they require all kind of weird stuff that you cannot fulfill inside QEM. You cannot fulfill inside our virtualized environment. Patch it, and then you will get your way through to run the entire firmware. So once you're able to run the firmware within the virtualized environment, that is where we can start to run the dynamic binary instrumentation. So, great.
Okay, so far you can already emulate the firmware. So that means you can introduce new tools inside the firmware, right? To run on our virtualization system. So remember that for guided fuzzer to run, we need to instrument the code, right? And remember that we do not have source code. So the question is how to build a guided fuzzer for embedded systems that work for binary only without having any source code. So because we need to instrument the program without source code, so we have to somehow have our own dynamic binary instrumentation. So the idea behind DBI is very simple. DBI is a method for analyzing the binary operation at runtime by injecting actual code into the program at runtime. So the idea is that the actual code is executed as a part of the original code without changing any context of the program. We don't change the behavior of the program. And talking about the DBI, we're talking about the framework. We don't talk about tools, not end user tools, but framework, so we can build our own tools on top of DBI. So the idea is very simple. On top we have the original code, for example, 5 instructions or 4 instructions, instruction 1, 2, 3, 4. Now we want to instrument our code, this code, so we can run our own code after instruction 1, after instruction 3, right? So the idea is that we can inject our own actual code into the original code after 1, after 3. So when you run that, we run 1, and then we run our own instrumentation code. And after that, we run 2, 3, and then we run our own instrumentation code in B, and we run 4. So the idea of DBI is very simple like that. But keep in mind that A and B, when we run A and B here, we do not change the original behavior of the program. That's the key point. So there are 2 main type DBI techniques. The first one is called just-in-time translation. So the idea is that we do not run the original code, but we translate this code into some other code, and we put the result into a buffer, and we run from the buffer. We do not run directly. We do not really run the original code, but you run the code in the buffer after translating it. So we can perform the translation on some intermediate language, like in the case of Van Green, or we can perform translation directly on the native code, like in the case of Dynamo Real. So we can see that the JIT technique is good because it has very good control on the code under execution. However, this technique is very heavy, it's very complicated, and very hard to do it properly. And if you look at all the existing DBI, like PIN or Dynamo, they are in development for like 10 years or more than that, but they are still incomplete, and they support very limited number of CPUs, like only Intel only. The reason is this technique is very complicated. The second thing of DBI is called hooking, which is a lightweight, much simpler techniques to design and to implement. For this hooking technique, we have less control on the code under execution, and you need to know in advance where to instrument. But it's much easier to design and implement. And on this work, we focus on hooking techniques. Talking about hooking techniques, there are 2 main type mechanisms. First one is inline hooking. So the idea is that we put the instrumentation code inline the original code. So you see that, okay, in this case, we put A and B, our instrumentation code, right after the original code, right? So and run 1 and A, and 2 and 3 and B and 4. However, this technique is very complicated because when you directly inline our own code with the original code, we ship all the code behind, around, right? For example, 2, we ship the position of 2. We ship the position of 3 and 4. And some code, when you ship the position, it doesn't work as original anymore. So we do not focus on this technique in our DBI framework. So here's our the technique we choose. This technique is called hooking mechanism. It's called detour hooking mechanism. So the idea is that we do not inline directly our own code behind the instrumentation code, but we clone out. So the idea is that we patch the original code, so it clone out to our callback somewhere else. As a callback is executed as a instrumentation code and a runtime. And in many cases, we cannot just clone from the original code to our callback, but we need to have some help from some executable memory called chamberlain memory. It's like a stepping stone buffer. So we put the callback into the chamberlain buffer, and we branch from the original code to the chamberlain buffer. So this technique is has some limitation compared to the inline hooking mechanism. First of all, this technique do not allow you to hook anywhere. First of all, if the basic block is too small, you override that basic block to control your trampoline buffer. You can override to the next basic block. So there's some limitation. However, this technique is very easy to design and implement. So that's why we chose and we went with this technique for our framework. So the idea is that we branch from the original code to the instrumentation code. So you can either branch to the trampoline, or you can branch directly to the cone back. So there are four main techniques for instrumentation: jump to trampoline, or jump to cone back, or cone to trampoline, or cone to cone back. So here the first technique, jump to trampoline. So on the left side you see the original code, right? And you want to instrument the green instruction. So the idea is that we allocate our own buffer named trampoline buffer in the middle, and we override the original instruction, the green instruction. So when we run there, we save the context because branching can change the context, and then we jump to the trampoline buffer. So you can see that when this code run, we save the context, we jump to the trampoline buffer, and we restore the context that was saved before. And again, we need to cone to the cone back, right? The cone back is provided by user. So before you cone to the cone back, you save the context, and you cone to the cone back. And after we come back to the cone back, we restore the context. And after that, after our instrumentation code is run, we need to execute the original instruction, right? But the idea is that we need to move the original instruction. We need to copy the original instruction from the original place to our own trampoline buffer. However, some instructions are very sensitive with moving like this. First of all, on the relative instruction, when you move from original place to the new place, it doesn't run anymore. You can break your program. So you need to relocate the original instruction before you copy that into the buffer. So after we execute the original instruction already relocated, we jump back to the original place. After that, everything is going on as normal. So this is the first technique, we jump from the original place to the trampoline buffer. Okay, so the next technique is that we do not jump to the trampoline buffer. We do not use any trampoline buffer in this technique, but we jump directly to the cone back. So you see that we save the context, and we override the original code with the jump instruction. We jump to the cone back. When we restore the cone back, restore the context, and execute the relocated instruction, and after we do something in the cone back, whatever, and we return. So you can jump, you can cone to the trampoline, you can jump to cone back. You can jump to trampoline or jump to cone back. So the next technique is called cone trampoline, because there are many two main type branching, right? Jump or cone, right? To change the direction of the code. So we can use cone to change the direction to the trampoline. So this technique is called cone to trampoline. So you can see that again we save the context, and we cone, we do not jump, we cone to the trampoline. So inside the trampoline we restore the context, we save the context before is the cone to cone back, and we cone to cone back, and we restore the context, right? So we run with the instrumentation, and we execute the original instruction already relocated, and we return to the instruction after the cone, and we keep going. So see that we do not change in any context when we run our interpretation code. The last technique is that we do not cone to the trampoline, but we cone directly to the cone back, right? So we do not use any trampoline in this mechanism. Okay, so the problem on the existing DBI is that, okay, before we did this, we consider all the existing DBI, and we saw that all of them has some issues that we do not like. First of all, on the existing DBIs have limited support for platforms. So for example, talking about PIN from Intel, right? They support, they work well on Windows, on Linux, but they do not work very well on Mac, for example. Dynamorio doesn't work well on Mac. Van Green doesn't work on Windows at all. So none of them work on every platform. The second limitation is that limited on architectures. Pin from Intel only work for Intel, and to some extent for ARM, but doesn't work for ARM64, for MIPS, for PowerPC. So it's the same thing for Dynamorio. They only support Intel and ARM, not other CPUs. Limited on instrumentation technique. So I introduced 4 main hooking mechanism, and all those DBI, they hide all the details inside. They do not expose outside, and they do not support all those hooking mechanisms. The last limitation is that all those DBI, they are designed for you, so you can easily use that to build your own tools. But they hide many details. So because they hide many details inside the core, you have very limited capacity to optimize the engine of the DBI. Okay, so because nothing works for us, we want something better for this specific case. So we design our own DBI framework named Scorpio. So there's some features. Scorpio, first, it's a kind of low-level framework, so you can build your application on top of this framework. And the application typically designs dynamic libraries, for example, DLL for Windows or SO for Linux, DLL for Mac. And at runtime, we inject these dynamic libraries into the target program. Scorpio works cross-platform and cross-architectures. So we wanted this for embedded system, but eventually invented and designed Scorpio, so it works for own card operating system. It works for Windows, for Mac, for Linux, for BSD, for Android, and so on. It supports all the popular CPUs. It works for x86, works for ARM, ARM64, MIPS, Spark, PowerPC, and a few others. And because we want various flexibilities and maximum optimization, so Scorpio support own card instrumentation I introduced before. And unlike many other existing DBI, you can find many existing DBI even open with source code on the internet, but many of them only allow you to instrument the function at the entry point of the function. So unlike that, Scorpio allow you to instrument at any address in the program, anywhere. We designed Scorpio to be very easy to use, but support own kind of optimization. So in some special setup, it can be like 100 times faster compared to any other things. So here's the diagram. You can see that we abstract away all the details about the OS, about the architectures, and all the OS, all the architectures come in as a plugin. So we support Windows, Mac, Linux, or BSD. We support all kinds of CPUs, ARM64, ARM, MIPS, Spark, PowerPC, and x86. Okay, so there's some details about how we design and implement this. First of all, we need to support cross-platform operating system, right? So talking about memory, we need to support Scorpio so it can provide, you can allocate a chamberlain buffer, it can change the permission from read-write to executable, and after that you can patch code in the memory. So different operating system has different way to allocate memory, to change the permission, or to patch memory. Okay, we need to support all kinds of CPU, right? And this is, depends on the CPU. Different CPU has different way to, different requirement for you to save memory, to save register, to restore memory, to restore registers. So we have to handle all of that. And not only about CPU, we also need to consider the calling convention, because each operating system has different ways to call the callback, right? So we need to save the context properly and we restore it properly. And that depends on calling conventions. It's pretty complicated. Okay, I think I should skip some details. You can look at the slides. So here's about how to support coding callbacks on card CPUs. So different CPU have different way to call the callback to insert element into the memory, to the stack, for example. Yeah, some CPUs very weird, like PowerPC is very weird, and it's got complicated to support to branch from the original instruction to the championing buffer. So we had some tricks to support PowerPC, for example. Scratch register. So because many CPUs like ARM64, MIPS, Spark, and PowerPC, they do not allow branch to indirect target in the memory. They only allow to jump to a rest, keep inside register, right? So in this case, we need to use some scratch register. So we store the target rest into some scratch register and we jump there. And that very much depends on CPU. One more thing, we need to patch the memory. We need to patch the original instruction. So it overrides original instruction, so we can execute our callback, right? So code patching need to be reflected in the each instruction cache, and this also depends on the CPU. Hello? First of all, x86, it doesn't have any instruction cache. It just overrides the original instruction in the memory, and that's it. But for other CPUs, we need to flush the cache. So once you override, flush the cache, and the CPU can recognize a new instruction. There's something in the implementation part. So first of all, we need to override all the original instruction in the memory. And by doing that, we override one or two instructions, for example. So we need to get the instruction boundary, right? Like one or two. And the amount of instruction to be overwritten depends on the CPU. For example, x86, because the instruction size is not fixed, right? So we need to use some disassembler to determine the instruction boundary. We can override one or two or more, it depends. So for this requirement, I use my own capstone disassembler, so we can extract the instruction boundary. The next part to do is that I need to override the instruction, because we need to relocate instruction, right? Once we copy it from the original place to the championing buffer. So we need to relocate, first of all, on the relative instruction. So in this case, we use capstone to detect the instruction type. It depends. And after that, we use our other framework, Keystone Assembler, to override, to rewrite the relocated instruction. So it works in the new place in the championing buffer. So you can see that actually Scopo is built on top of two frameworks, Capstone disassembler and Stone assembler. And because these two frameworks work cross-platform and cross-architecture, that's why Scopo work on on-cap CPUs and on-cap operating system. Okay, so some other things about we need to do in Scorpio, like code analysis. Customization. Okay, so as I said, because Scorpio is very flexible and allow on-cap optimization for you to build a fast and powerful fuzzer. So we provide API so you can do on-cap optimization. You can optimize callback, optimize the chamberlain, you can optimize the scratch register, how you save store context, and so on. Okay, so now we have our own DBI, and we can use this DBI to instrument the binary of the embedded system, right? So what to do with that? We went on to build our own fuzzer for embedded system, coverage guided fuzzer. Okay, so the idea is that we do not build our own fuzzer from scratch, but we build on top of a fuzzer which is very powerful and very mature fuzzer. So we do not do from scratch, but we build on top of AFL. But remember that AFL doesn't support closed binary very well. So our extension on AFL need to support fuzzing the binary, right? So we use our Scorpio DBI to support and instrument target binary running inside the fuzzer. Just some features we build for our fuzzer. We support selected binary fuzzing. That means we can focus on fuzzing only a part of the binary, not the whole binary. We support persistent mode as well. And besides that, we combine our own fuzzer with some very advanced techniques, like we combine that our own fuzzer with simulate execution, or combine static analysis, so our fuzzer can penetrate deeper into the program and find more code. So to design the fuzzer is like this. It's pure shopware based. We do not rely on any CPU features, right? We use just pure binary, pure shopware based mechanism. And our fuzzer is cross-platform. We work on all the operating system. This fuzzer work for not only for embedded system, but only work for other platforms like Windows or Mac or Linux or anything. It built on Scorpio, which support many CPU. So our fuzzer also support many CPU as well. It's ARM, AC4, MIPS, PowerPC, Spark, and all those embedded system. Okay, binary support, of course. And we build our fuzzer, so it's fast and very stable. It's much faster than other fuzzer you can experiment on in the public now. And it's very stable. Okay, talking a bit about implementation. So we reuse a fuzzer. We do not change the core design of FL at all. We use the fuzzer itself. And remember that in the design, if we want to fuzz a program on the FL, right, we need to compile from source code to introduce instrumentation into the target binary. But because we do not have source code, we only have target binary, right? So we build our own instrumentation using Scorpio, as I explained. So the instrumentation part is compatible with FL. So we just reuse FL, we do not change anything. But the instrumentation part is compatible with FL. So that's how we can reuse FL. The point about Scorpio is that we need to tell it where to instrument, right? So we need to fuzz a program, we have to perform static analysis for this program before we run the fuzzer. And after static analysis step, we can locate the program in the program where we want to instrument, and we pass this information where to instrument to Scorpio, so Scorpio can inject the hooks inside the program when they run at runtime. Yeah, and at runtime the hook come back instrumented by Scorpio, just update execution context like the usual in the typical scenarios in FL. So we add the same memory whenever we reach some basic block, for example, so FL knows what's going on. And because we use very lightweight Scorpio DPI, so as a result, our fuzzer run at a near native speed very fast.
Okay, I lie. We don't have demo, really. But we do fast one of the favorite Wi-Fi router in China. I'm not too sure this part of the world whether it's that famous or not. And we discovered few interesting things. Of course, we get a RCE. Okay, we get a buffer overflow, and then we craft some shellcodes and all these things, and then we get a RCE. But one interesting about this vendor, it's you have one exploitable bug in the international version, which is quite obvious. And on the China edition of the firmware, they don't have that particular bug, so don't quote what I said. It's not good. And of course, on their own Chinese version, we do discover some other bug which is still exploitable, but it's not as obvious as the international version. So you can see we actually inject command, we turn on the telnet on port 4444, and we got telnet are being activated inside the system. So this is fast by the thing that we have built together. All right. So the conclusion is, we do have certain issues on the closed source software. We still have issue on the DBI that are currently available out there. And then fuzzer is not strong enough, so we built a firmware emulation, so we can do a DBI, we can do a guided fuzzer for the entire system. So we solve 3 issues by using 3 different tools. Okay, the emulation, the Scorpio DBI, and then finally the guided fuzzer for embedded system. All right, so yes, we built a smart fuzzer, not only smart, but one of the fastest fuzzer in the world, I believe. If somebody want to challenge me, I will go away from here. Okay, so we emulate firmware. We have a cross-platform architecture fuzzer, okay, and a DBI. Of course, we support binary only, and yeah, we found quite a fair bit of bug, and the one in the Tenda router is one of them. We still have 3 minutes for questions. Yes, we are not releasing it yet, just in case you ask. So, questions.
Okay, thanks for the talk. Yeah, we have one question coming up.
Yeah, I have another question. It's not about releasing the code, but actually the static analysis step you mentioned to implement the hooks, is that automated or do you need to do that by hand?
Okay, we use some static analysis tool to analyze the program, but we still need to do some manual work, so we can focus where we want to focus the fuzzer on. For example, we just want to focus on the parser part, right? So we locate the area, and we know from here to here we need to focus our fuzzing, and we instrument those basic blocks. And once we know what we need to do, it passes the information to the fuzzer, so it knows where to instrument the code.
The thing is, with IoT devices and an embedded system, it's a fairly huge binary that you're normally looking at. So they have the web servers, they have all kind of weird stuff in there. So it's good to analyze before you need to extract out the part you need to fuzz, then only you fuzz. You don't want to fuzz the entire 4 meg, 8 meg binary just for you just to fuzz it.
So actually you can, okay, if you're lazy or you want to do quick, you just instrument everywhere, right? That's also possible, but you want to build good, productive, quick, and yeah, nice fuzzer, you need to do some manual work to analyze the program before that. Anything that applies for own car fuzzer, not only this.
Thanks.
Right.
Any more questions? Okay.
Okay.
So thank you. And,
Okay, thank you.
Thank you.
a big round of applause.